This is the third video on revision of A-level trigonometry. And you're reminded that the videos are aimed at students doing things like A-level mathematics or equivalent courses of around the age 17 to 18 years old. Our intention is not so much to teach trigonometry, rather as to demonstrate how you might solve typical problems that come up in examinations. However, in order to solve problems, it's important that we first say what are the key things that you should know. So the first part of the video is going to briefly go through how the trigonometrical functions are defined. Now, when answering a question, what you need to do is, of course, first look at the information provided in the question, but secondly, equally important, you need to say what information or knowledge it's assumed you already have. And that's why, for the first part of this video, we're going to consolidate and say what information or knowledge will the examiner expect you to bring into the question. And if you focus on that, answering the question becomes straightforward. First then, let's look at some definitions. Now, this video is going to focus on cosine. And so what we want to do is ask ourselves, how is cosine defined? And I'm emphasizing the word defined. It's not something to understand, it is a definition. And in particular, we're interested in what happens to cosine outside of the 0 to 90 degrees. Now, within 0 to 90 degrees, you'll all be familiar with this definition for right-angled triangles. Cosx equals adjacent over hypotenuse, and you'll see there's a nice right-angled triangle in here, and you'll notice, of course, cosx is the adjacent of this right-angled triangle. But what do we do if we want to go beyond 90 degrees? Well, the easiest way is to look at the definition of cos, or a more general definition for cosine, and the general definition is based on a circle of radius 1, and you'll see that's what we've plotted here. And what you do is you take the horizontal projection of a point when that point goes round the circle, and obviously the x is marked in here. So you can see for 0 to 90 degrees, the horizontal projection clearly gives you cos x. What happens if you want to go beyond 90 degrees? Well, all we do is we consider a different point somewhere else on the circle. So you'll notice I've drawn a different point, and for this different point I've got a different angle x, and I've got a different horizontal projection. There it is. And so cosx is simply defined as the magnitude of that, or not the magnitude, the value of that horizontal projection. So what we want to do next is say, okay, given this definition for cosx, can we actually understand a bit more about what the cosx function looks like? First then, I'm going to look at angles between minus 90 degrees and plus 90 degrees, and you'll see I've drawn a circle here to demonstrate what's going on. So I've got an angle x, 0 to 90 degrees, and if I go down, then the corresponding angle must be minus x, because I've gone in the opposite direction around the circle. So this direction gives me a plus x, and this direction, opposite direction, gives me a minus x. Now what you'll notice is if the magnitude of x and minus x are the same, clearly they must give you the same horizontal projection. I hope that's obvious to anyone viewing this. So you're going to get things like cos of 20 must be identical to cos of minus 20. The horizontal projection for plus 20 degrees is the same as the horizontal projection for minus 20 degrees. And so if I mark a point 20, and this value up here is clearly cos of 20, I must get the same value at minus 20. So this is the x down at the bottom. So cos of minus 20, cos of plus 20 must be the same. Now clearly I can do that for other values. I can look at minus 50 degrees and plus 50 degrees, and again you can see they must give you the same value. And so we end up with a general observation that cosx equals cos of minus x. Now, two values which are important to notice is I've put down here in the bottom left hand corner of the screen. If you take an angle of 0, that's going to put you here, then clearly the horizontal projection is 1. If you take an angle of 90, which is up here on the circle, then clearly the horizontal projection is 0. So you get cos 0 is 1 and cos 90 is 0. What happens now if I want to go outside of the minus 90 to plus 90 degrees? So I'm now going to look at 90 to 180 degrees or minus 90 to minus 180 degrees. So here I've marked in an x, and you can see this x is about 120 degrees. Or I've got an equivalent minus x, which is approximately minus 120 degrees. So if we go back to the definition was that cosx is defined as the horizontal projection. And you can see again, these two give me the same horizontal projection. I could work out what that is. I'm not going to worry too much about the fine details at the moment, but clearly you can see if I take 120 degrees, which is somewhere about here, and I take minus 120 degrees, which is somewhere about here, so this is the x-axis, what do you notice? These two have got the same value. And so we end up with the same formula that we had before, that cosx equals cos of minus x. Now the other thing you'll notice is there's a sort of symmetry about the value. So if I clean up this circle a bit, and what I'm going to do is add another value on here, where this is 60 degrees, and this angle in there is 60 degrees, and hopefully what you can see is that cos of 60 equals minus cos of 120. And what that's telling you is there's a sort of symmetry about here. So if I go 30 degrees to the left, or I go 30 degrees to the right, I get the same magnitude. So there was cos of 60, and there's cos of 120. So they've got the same magnitude, but the opposite sign. And that sort of symmetry about 90 degrees or minus 90 degrees is something that you may find useful from time to time. So what about periodicity? Well, it was proved in the previous video that cosx equals cos, or rather, values repeat every 360 degrees, so cosx must be the same as cos of x plus 360. So for example, if I take x equals 0, I get 1. If I go all the way up to 360 degrees, I get 1. If I go all the way up to 720 degrees, I get 1. So you can see there's a repetition every 360 degrees. Similarly, I could take a point here at 60. I could add 360, and that brings me to this point, which is 420. Or I could add 360 again, which brings me to this point, which is going to be 780, and so on. So the values repeat every 360 degrees, and that's quite a useful pattern to recognize. So a summary then. In every 360 degrees, each value appears twice. The positive values appear in minus 90 to 0 and 0 to 90. So you can see minus 90 to 0, 0 to 90, there are two partnered positive values. So anywhere in the 0 to 90 and minus 90 to 0, you can see there are two partnered values. The negative values appear in the quadrants minus 180 to minus 90 and 90 to 180. So you can see again, you get partnered values, but here they look a long way apart, but you can see they're simply the negatives of each other in terms of the angles. Right, let's move on to some questions then. How would we find the solution for a question like this? Cos x equals minus root 3 for 2 for x between minus 180 and 720. And the key thing to remember is when you answer questions like this, start with what you know. So what I'm going to do is I'm going to say what I know is a sketch for the cosine curve. So I'm going to start by doing a sketch of the cosine curve. Here it is. Now once I've done the sketch, I can actually identify this value on the sketch. So it's somewhere around here. Minus root 3 over 2 is somewhere around here. So I can see there's a solution here, 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 and so on. I can immediately see where all of the solutions are. And what this means is I'm not going to make a silly mistake when I answer the question. I know roughly what values I'm looking for. So let's start now by getting a simple value. So cos x equals minus root 3 over 2, and if you stick this in your calculator, you'll probably end up with something like x equals 150 degrees. However, I know how the partnering works. There's my 150, so I must also have a solution at minus 150, because x and minus x give you the same cosine. So I'll write those two down, 150 and minus 150. The next thing I know is solutions repeat every 360 degrees, so I can just add 360. So if I put over here a note, add 360, that means you'll get the same solution at 410 degrees. You also, sorry, isn't it 410? That's a bit careless of me. I meant 510. I should learn how to add, and you can see that that's this solution here is at 510. If you add 360 to minus 150, what are you going to get? You're going to get 210. And you'll see the 210 is this one here. Okay, I put the 510 in the wrong place. It was there. If I add 360 again, you're going to go to 870 or 570. Now, let's look back and see what we were asked to do. We were asked to find solutions in this region here. So what I can do is I can say that's a solution, 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 but clearly this one is outside of the range that I was asked. So I've got 5 solutions. Next question then. Find the solutions for this. Cos 3z plus 40 equals 0.2. And again, I recommend you start by giving yourself a quick sketch. So here's my sketch of the cosine curve, and again what I'm going to do is I'm going to mark my point 0.2 and find out where the solutions are. So I've got one here, one here, one here, one here, one here, and one here. So I can see where my solutions are. So if I define this thing in the brackets to be something like y, then if I'm solving cos y equals 0.2, that gives me y equals 78.5, or, because we know the way they're paired, minus 78.5. Now, y is 3z plus 40, so what I could then do is write 3z is going to be 38.5, so I subtracted the 40, or minus 118.5. So that gives me the default solutions to start from. And the next thing is we said, okay, if you want to get the repetition, you've got to add 360 degrees to each of these. So if I add 360 to 38.5, I get 398.5. If I add 360 to minus 118.5, I get 241.5. If I add 360 again, I get 758.5, or 601.5. And then finally, of course, we want to find z, so we need to define each of these by 3. So I'm going to get z equals 38.5 over 3 is 12 and 5/6. 398.5 over 3 is 132 and 5/6. And 758.5 over 3 is 252 and 5/6. The minus 118 over 5 I don't need to do because I'm looking at a range starting from 0 degrees. 241.5 over 3 gives me 80.5, and 601.5 over 3 gives me 200.5. And again, I now look at what range I'm interested in. I want only angles less than 180, so I don't need that one, and I don't need that one. So I've now got 3 solutions.